Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 1. Trapezoidal rule with and without incorrection. Numerical integration is needed for several reasons. Here are the primary reasons why numerical methods for integration are important. In cases we are unable to find analytical solutions for special functions. In real-world problems, the integrands can be complicated or involve piecewise functions, discontinuities, or noisy data, making it difficult or impossible to integrate analytically. Integrals with multiple dimensions are often difficult to solve analytically. To evaluate definite integrals with complex integral limits, it is often easier to use numerical integration rather than finding a closed-form solution. In most cases, we deal with functions that are defined by discrete data derived from experiments, for which analytical tools are useless. Consider a continuous and integrable function f(x), defined on the closed interval from a to b. The definite integral of f(x) from a to b, corresponding to the area depicted in the figure, is expressed as follows. When the true value of a definite integral cannot be determined, the area of the bounded region under the curve is approximated. The bounded area is divided into a number of panels, and the endpoints are connected with straight lines, creating trapezoids. For one panel, we have a single trapezoid, and so the area of the trapezoid becomes, where Fi denotes Fxi. Also recall the formula for the area of trapezoid. Notice that the remaining area between the line and the curve, which is not taken into account in the approximation, is quite large. This is our approximation error. Now, consider a two-panel integration. We approximate the area of each panel with trapezoids as follows. Substituting A1 and A2 yields the following simplified expression. Here, notice that the size of the area between the curve and the lines, which corresponds to the approximation error, decreases by increasing the number of panels. For a four-panel approximation, the panels are likewise approximated with trapezoids. Substituting the approximate values gives the following simple expression. As can be seen, by doubling the number of panels, the area between the lines and the curve has decreased noticeably. For uniformly spaced end panels, we obtain a generalized expression, which gives the in-panel composite trapezoidal rule. Clearly, as the number of panels is increased or as h goes to 0, the numerical integral approaches the true value. But, due to requiring excessive CPU time, it is impractical to use an infinitely large number of panels to estimate the definite integral of a function. Hence, the composite rule is applied with a finite number of panels that provide an acceptable approximate value. The truncation error for an in-panel composite trapezoidal rule yields the following expression. Here, it is clear that the trapezoidal rule is second-order accurate. With the proportionality constant k involving the magnitude of f double prime xi. Xi is some point between a and b, whose exact location is unknown, but exists by the mean value theorem for integration. We use this term to find an upper bound for the error. That is why we determine the maximum value of the second derivative over the integration interval. Finally, we can express the in-panel composite trapezoidal rule including the order of error as follows. The order of error of the trapezoidal rule can be made fourth order if the error, Rn, is also incorporated into the composite rule. To include this truncation error term into the numerical integration, we apply the mean value theorem to the first derivative of f as follows. Upon substitution of the mean value theorem, the error term becomes Substituting this term into the trapezoidal rule results in the following expression, which is a fourth-order accurate approximation referred to as the in-panel trapezoidal rule with incorrection, since it only requires the derivatives at the endpoints. The advantages of the trapezoidal rule are: the trapezoidal rule is simple and easy to apply. It is a weighted sum of the integrand for a specified number of integration points. CPU time is the minimum for uniformly spaced discrete functions. There is no restriction on the number of panels to be used. As the number of panels increases, the numerical estimates of a continuous function always approach the true value. Since they are second and fourth order accurate methods, Tn and Ctn give the true integral value for polynomials of degree m1 and m3, respectively. Error analysis is straightforward. The disadvantages of the trapezoidal rule are: the integrands must be continuous, i.e., it does not work for integrands with singularities at the endpoints or within the integration range. The rate of convergence of Tn is rather slow. Endpoint correction formulation, CTN, cannot be applied to the integration of discrete data sets. Integrands depicting oscillations or sharp changes require a large number of panels to yield sufficiently accurate estimates. As a numerical example, let us consider evaluating the following integral using the composite trapezoidal rule with uniformly spaced n equals 4 and 8 panels. We will repeat the numerical integration using the composite trapezoidal rule with incorrection and estimate the theoretical upper bounds of the numerical error for the integrations performed. The true integral is natural logarithm 2. For n equals 4, we construct and tabulate the abscisses and the ordinates. We express the trapezoidal rule as a weighted sum, where the weights placed in the fourth column are 0.5 for the first and last data and 1 for the others in between. The last column is the product of the functions in each row and the corresponding weights. The last column's sum gives the parenthetical term of T4. Multiplying it with H yields T4, which is 0.697024. The corresponding true error becomes minus 0.003877. Now let us investigate the upper bound of error for the 4-panel estimate. To calculate the error, we need the value of f'(c), which is the only unknown term here. So to be conservative, we will replace this term with its maximum magnitude. We note that f' is a decreasing function whose absolute maximum value of 2 is at x equals 0, which we verify by plotting it in the range from 0 to 1. Then we obtain our 4 to be 0.0104167, which is larger than the actual error. Next, we estimate the integral using the trapezoidal rule with incorrection. To calculate the correction term, we need the first derivative of fx, which is easy to obtain. Thereafter, we evaluate f'1 minus f'0, which leads to 3/4. To estimate the integral with the incorrection, we simply add the correction term to T4, which yields 0.693118. The true error is then found to be 2.94 times 10 to the minus 5. This is a significantly improved result compared to the T4. Now we will tackle the trapezoidal integration process for 8 panels. We first calculate the xi's and corresponding value of the function at each xi for I equals 0 to 8. The weights placed in the fourth column are 0.5 in the first and last rows and 1 elsewhere. The last column contains the products of the weights and abscisses. Multiplying the column's sum with h gives the estimate for the trapezoidal rule. Recall that we needed the maximum magnitude of the second derivative, which was 2, to estimate the upper bound of error for T4. When we make use of this value, we find that the upper bound of error to be minus 0.002604, which leads to the true error for T8 as minus 9.75 times 10 to the minus 4, as it should. R8 is larger than the true error. The trapezoidal rule with incorrection is obtained by simply adding the correction term to T8. Recall we had already evaluated the first derivative and found that f'1 minus f'0 was 3 over 4. Hence, using this, along with h equals 1 over 8, we find the CT8 to be 0.693145, which corresponds to the true error of 2.18 times 10 to the minus 6. With this note, we conclude this video session. That is all for now. See you next time with another topic. Bye.